So good morning, everyone. It's a great pleasure today to have this Netpore webinar session and to welcome uh, Dr. Brice Lebon. Brice Lebon is an associate professor at the University of Tours in France, where he teaches power electronics and electrical engineering. He studied mechatronics at the École Normale Supérieure and he obtained his PhD in microelectronics in 2016 from the University of Rennes in France. After 2 years as research assistant at the University of Surrey in UK, he joined the Grayman Laboratory in Tours, and since then, he dedicates his research to porous semiconductors for energy application, and in particular, his work aims at developing more responsible processes for nanomaterials and thin film deposition. And today, Brice will be talking about ultrasyn coating, the next step for porous semiconductors, as a question. Brice, please.
Yes, thank you for the introductions. Thank you for having me. So yes, the title of the presentation is ultra-thin coating the next step up for porous semiconductors? I will try to answer this question, but of course it's an open question. And I subtitled this presentation towards CO2 valorization. You will see why, because I think it's a nice application for our main topic, porous silicon. So as to complete your introduction, so yes, I'm associate professor at the University of Tours. So Tours is located southwest from Paris, like 1 or 2 hours. It's a very nice city, old town, and it's in the Loire Valley. So the Loire Valley has nice castles, nice vineyards. So you're all welcome to visit at some point. So for me, it looks more like this. So we have nice facilities also shared with ST Microelectronics and a technological platform called CERTEM. So we have everything to fabricate components and energy-related devices. That's our main focus at Grémont. But also we have place, of course, for more academic work. Today's presentation will develop like this. So first, an introduction on the use of porous semiconductors, and especially two I want to talk about: porous silicon, of course, and porous silicon carbide. So you all know this, but I will, of course, focus the presentation on what's interesting for the rest. I want to present also the applications and motivations of this work. And in particular, the CO2 valorization that I try to focus my research now. I will talk about advanced coatings, so a short review on what's existing now, and I will focus, since we are talking about ultra-thin coatings, I will focus on atomic layer deposition, which is a very nice tool for porous semiconductors. I will, of course, develop how to fabricate and characterize porous photoelectrodes for CO2 valorization. And of course, I will finish with perspectives and a conclusion. So regarding the use of porous semiconductors, you all know porous silicon. I'm not gonna spend more time explaining how to fabricate it, but I think it's very nice, a very nice material to develop optical devices. So in the literature, you find many examples, of course, of sunlight energy-driven applications. So if you etch the porous silicon, you can nanostructure it and have nice properties like you have for rugged filters. Or you can even fabricate devices. So it's not just a material that has interesting properties. You can really use it for the industry. So since the 90s, we know how to fabricate electroluminescent diode, LEDs. So it's very nice, and you can have it in many different natures. So you can have it in a 2D or 3D structures, so thin films and so on. You can have it as 1D structures. What I call 1D is just nanowires, but they can be porous, so you can have other properties thanks to the porosity. And you can have them after grinding or different techniques. You can have them as nanoparticles, so as 0D structures. And with that, you can do, if I look at the optical properties, you can have photoluminescent properties or light harvesting properties. And this is the second one I'm interested in this talk. So for instance, if you look at this piece of porous silicon, so if you just try to plot the reflectance of the silicon, you have something like the blue spectrum. And when it's porous, you can see that you can already trap a lot of light, and this is pretty gray. And of course, we all know that we can have much darker porous silicon. So you can really trap the light, and it's of course good for light harvesting applications, because you know that silicon itself is the most used material for solar panel and sunlight harvesting. So porous silicon has, of course, many capabilities. And it's not the only one. It's porous silicon. You can really use it in the industry. So people tend to say, and we also talked about it during last PSST. Porous silicon struggles a little bit to enter the market. But it's very strange because our lab, so the work from Gaël and Thomas that you probably know, showed that you can do devices. So you can integrate inductors, for instance, diodes, capacitors, sorry, and you can improve a lot the quality factor of the radio frequency devices when you use porous silicon. So the thing about it is you can both use optical properties, and you can also integrate it in devices. So when I joined the lab in 2019, I said, okay, there's space for many things with this material I didn't know before. So that's from one side. From the other side, we developed recently, we've been developing porous silicon carbide, which again is not so common. So this is something we do with the University of Catania in Italy. With or from silicon carbide, you can also etch it by electrochemical etching and obtain different shapes depending on if you etch the silicon phase or the carbon phase. And it's very interesting to try to use this semiconductor, because it's a wide bandgap semiconductor, so 3.2 eV, and it can probably offer, of course, you already understand maybe where I'm going. You can use it for optical properties. And it's not so common to use porous silicon carbide within devices. So of course now it's really developed for power electronics, but not porous silicon carbide, only silicon carbide. So I think there's space also for that in the industry, even though we need to improve it a lot. Actually, there is a nice recent study that talks about the opportunities for silicon carbide or porous silicon carbide, and especially in the field of catalysis. It's something that we developed with this team in Catania. And I think there is a lot of space, because as you can see, you can form porous silicon carbide as catalyst or as support, and in a quite wide range of size, so or pore size. So I think it's It's gonna be something in the next years. So you already had two presentations, I think, about this material in PSST, in last PSST, but I think it's gonna grow a bit. So it's very interesting. So you can see here how it looks like. And again, 10 years ago already, Gael showed that you can improve the quality factor of devices designed on top of porous silicon carbide. So it's very interesting. To conclude on that, on the fact that I think you understood now, but on the fact that it can be really industrially viable, we use at 6 inches etching cell at the Gremon laboratory. So it's really compatible with the industry. And of course, reproducibility and homogeneity is something important for industry. So we have also not to focus on small samples, but it's possible to make them larger and to convince the industry that we can use this material for the market. So to conclude on the drawbacks and the good points of each of these two materials. So porous silicon is easy to etch. We all do it, almost all of us. Porous silicon carbide is not so easy. It needs adaptation, but when you master the process, it's simple enough. The porous silicon is chemically unstable, so you often need something to stabilize it. So that's what we're going to talk about after. While the porous silicon carbide is very stable, that's really good. Porous silicon can be brittle also. That can be a problem depending on the porosity you need, but it's easy to handle, so that's good. Porous silicon carbide remains hard, less than silicon carbide, bulk silicon carbide, but it's still good and it's very easy to handle too. Porous silicon can have a decent specific surface and very high specific surface if you use porous nanoparticles, for instance. For porous silicon carbide, it's good. It's not as good as the porous silicon, but it's good. So I already said it struggles to find a market, and so I put it in green for porous silicon carbide. No market yet, I don't think so, but it's a good opportunity for us. So to sum up, we have good optical and electrical properties for this material. They are compatible with the microelectronics industry, and it's a versatile mechanical support for catalyst. And we just need to balance the drawbacks to find a good application. And the one that motivates me, or has been motivating me for the last 3-4 years now, is the CO2 valorization. Some people call it also artificial photosynthesis. So I'm going to quickly introduce this topic. So artificial photosynthesis is really the artificial part of the natural photosynthesis, which all the plants are performing. So basically, with water and sunlight, they are able to fabricate energy, and using CO2. So they convert it in carbohydrates thanks to this light transformation, which is called photosynthesis. For the last 20-30 years now, many people have been trying to develop artificial photosynthesis. Some people call it artificial leaves. I mean the devices they make. So basically, you use catalysis, use supports to harvest the light. Can be nanowires. The catalyst can be based on different oxides mainly. You see them here, and we need to perform two reactions. One to produce oxygen or hydrogen, and one to produce a fuel. So it's a quite complicated system. You need proton exchange between the two faces of the leaf or the device. So it's a very nice challenge. And here on this illustration, you can see nanowires. but you can already imagine that you can use a porous material. And actually, porosity can be helpful to exchange the protons. So we have a couple of examples of well-developed systems. For instance, the Mitsubishi lab is developing devices. You can see it there under the light. And we have a system at Toyota of 1 square meter. So in Asia, they've been pushing the technology already quite a lot. And there are also a couple of teams in the US, but I think in Europe we're still a bit back on this application. So there's place for improvement, and I think it's really motivating. And what motivated me actually was this nice paper from Jan Ronget in Belgium, so 10 years ago already. And he said, okay, we should invent a structure. So he was doing a review on monolithic cells for CO2 valorization. And he said, okay, we should perform something like this. So a system with porosities, and then you could harvest the light at different wavelengths. And why not porous silicon? So this is all hypothetical, right? But it's very nice. And on the other side, you could use, why not carbon nanotubes with catalysts on top, and we could perform the CO2 reduction to form a fuel. Okay. So this was really interesting for me because I said, okay, that's very challenging to form such pores, and we could imagine growing nanowires, and I thought it was great. But of course, to perform this reduction of CO2, you need to exchange 8 protons and electrons, and for that you need to adapt the band gap of the system. Okay. So I'm not entering the details of this reaction here, but basically you have some materials that have catalytic, photocatalytic properties. They are all semiconductors. They can be titanium oxide, hematite, porous silicon, of course, or silicon has this property also, or copper oxide. And depending on the band gap alignment, you have more or less favorable materials. But anyway, if you just want to use the sunlight to create this electron hole pair generation, you need to fine-tune the band gap, right? So it's possible to do it with only porous silicon, but I think, and you understand, you probably need some coatings. So we try to develop photoelectrocatalysis applications, integration of the system, because it's something we do more with the industry, and of course prototyping to try to make a big cell. Okay. So of course we need to use ultra thin coatings or thin coatings, and you will see why ultra thin later. We should use them as green as possible because, to be honest, this kind of reactions so far are very poor in efficiency. Okay, so we need a lot of improvement on that. So if we are not very efficient, we at least should take care of the I would say the green side of the process. Okay, we should avoid using nasty material. They should be earth abundant, and if possible, if we work in Europe, available in Europe, and as efficient as possible. Okay, so there is all this work ongoing. So we try to work on each of these bits, right? So starting from the development of the photoelectrodes with different catalysts, and then we need to scale it up to the pilot plant. Okay, this was one of the projects we were trying to develop. But of course, we are at the very beginning. So today I'm focusing only on this part, so the electrode assembly. Okay, and the question is, what is the potential of the coating for porous silicon development? Because mainly of the people, most of the people that work on photoelectrode development are from chemistry. Okay, so they have their view. which I'm not gonna criticize here. Maybe probably some of you are chemists, right? But yes, sometimes I think it's possible to have a very different view coming from the semiconductors and the industry, the fabrication. I think it can lead to, to good things. Um, so I'm going to talk about the possibilities we have to perform these coatings. So I'm going to do it quickly and not entering the details, but it's possible to coat porous substrates with a technique with wet coatings. And one of the technique is the layer by layer deposition. You might know it. It's just a dipping process, and you can do it layer by layer. So it's very slow, unfortunately. It's very difficult to control the thickness. I guess specialists can do, but it's not straightforward. And it's unfortunately limited to organic materials, which restrains a bit the possibilities. There is another technique called successive ionic layer adsorption and reaction, also called SILAR. Is really promising, still quite new, but it's very tedious method. So again, it's specialist, it's technique of specialist at this stage, and not yet really used in the industry, of course. And it's hard to find in the literature deposition rates. So I don't have it, but again, I suppose it's quite slow. You of course have electrodeposition, so it's very famous and technique that has been used for many years. So it's pretty fast. You have fine control. It's possible to fill tubes to form nanopillars, for instance. We often have this kind of applications or presentations in either Netpore or PSST seminars. So it's great. But you need a conductive substrate. So that can be an issue. So that's the three techniques I'm presenting for the wet coatings. You of course have a lot of different ones or variations. Okay. You also can use dry approach, which is more, closer to the industry, the closer from what we are doing in tours and many of you working in clean room facilities, for instance. So you have PVD, CVD, PLD, and ALD. I don't know if you know all of them or if you're familiar, but I'm not gonna comment this. But of course, ALD, so I'm just going right now to the comparison, is ALD allows more conformal deposition when you have cavities, right? So cavities is also porous silicon, right? Or porous materials. And it's much more difficult when you use PVD, CVD, or PCVD, for instance, with plasma. It's much more difficult to have conformality. So I think for porous semiconductors, you can prefer ALD if you want dry deposition. So there is this interesting graph often used in the ALD community. So you can have very high step coverage with ALD or PLD. But of course, it depends on the deposition rate you want. So you have less step coverage with PVD, but you go very fast. So you can also consider using PLD or CVD if necessary, right? So you have here some examples of why ALD can be nice for porous silicon. Here you have high aspect ratio trenches in a device. So with PVD, you clog the pores and you can't really have a good pore filling. CVD would clog porous silicon. That's something we've done in our lab. And when you use ALD, you can nicely coat the pores down to the bottom, which is not so easy. So of course, I'm gonna focus my work on the use of ALD now. And and I think this is one of the most suitable for industrially viable photoelectrode. Okay, wet coatings can be much cheaper and very efficient too. So it's something we try also in collaboration with Joaquim Leitao in Aveiro in Portugal. But as would say Lionel Santinacci, you shouldn't have religion in science. It means I'm focusing my work on ALD, but it doesn't mean other solutions are not good, of course, right? So keep doing what you are doing if you like it or if you think it's good. But for our application, I think ALD is good. So ALD, to quickly present it, is a reaction, it's a chemical reaction with the substrate. So when you have a substrate that can have cavities, you necessarily have a chemicals at the surface. And first, to do an ALD cycle, you first pulse a reactant that will be adsorbed at the surface of this material. Then you have a purge cycle where you remove all the species that didn't react with the surface. Then you pulse a second reactant that will form a new material, a single layer of the new material with the reaction with the first reactant, and then you purge and you obtain this first atomic layer, and you can do as many cycles as you want to form atomic layer by atomic layer deposition, right? So now I'm presenting what we are doing to coat porous silicon to try to perform the best possible photoelectrode. That should so this coating layer should be protective because we know that porous silicon is chemically unstable, as I said at the beginning. So if it's chemically unstable, you need to passivate it. Okay. Then, if possible, you should have a high catalytic activity, so you can perform CO2 reduction or at least a chemical reaction at the surface of the porous material. Again, the porous material is also chosen for its high specific surface, and you should be able to perform optical band gap adjustment to perform the desired reaction. I'm not saying I'm gonna manage to do all of this, but we are trying, right? So the challenge is to do the good trade-off between the passivation, the protection of the porous silicon, but keeping the transport, the charge transport for the good generation of electron hole pair. So the method we have, so initially we're gonna check if it's actually protective. So the question we ask is how thin should be the ALD material to keep protecting the porous silicon. So we deposited less than 1 nanometer of titanium dioxide, which is a good photocatalyst. It's known for that. Around 1 nanometer and around 10 nanometers. So we compare three thicknesses deposited by ALD, and then we exposed our substrate to sunlight, and to water during 29 days. Okay, so a month within the water, and of course you would expect the silicon to oxidize. And we've made systematic measurement by infrared spectroscopy, checking the silicon oxide silicon bond area to see the evolution of the oxidation. Okay. So first, of course, we checked that we were able to coat the pores, so we made it successfully. And interestingly, you can see that you have this bowl-shaped titanium dioxide, which is good for photocatalysis. So it's not really something we mastered initially. We could discuss later why it formed like this. But for the thicker layer, so the 10 nanometer, we had these balls that are very good for catalysis. This is a TEM of the two other, for the other deposition, the thinnest one. So we can see it's less than 1 nanometer. It's non-ball shaped, and it's but it's quite rough. You also see this roughness. So this was performed using only 5 ALD cycles. Okay. And this is the image are done on flat substrate. It's very complicated. We are still working on that to image porous silicon. Okay. And then to check if we were actually depositing on the porous silicon, because we couldn't see it by TEM or SEM. So we've performed with the Cytec, so with Kaushik Baisha and Jan Matsak, we perform XPS measurements on the thinnest layer, the middle one, and the thicker layer, which is still quite thin. And we observed we had indeed titanium dioxide even on the thin layer, so it was possible to deposit it. So that was really a success. And then we started checking for 29 days if it was actually oxidizing. So here you have the bare silicon. Of course, we need to compare it with bare silicon, and you have the 29 days here, and we focus here on this wavelength that correspond to the peak related to SiO-Si bonds. And you can see there is an increase. So after the first etching, you can see there is no peak. And after 29 days, you have this increase of the peaks. So of course it's oxidizing, and there is a slight shift because the angle of the bonds is moving with the time. So this is really documented in the literature. If you check the 1 nanometer, you can see it's not obvious to see an increase of this bonds. So I don't think it oxidizes. This is a random distribution of the absorbance, so no particular oxidation. Of course, not on the 10 nanometers. And the most interesting result here is it didn't oxidize neither after 29 days with the thinnest layer, of 5 ALD cycle. So that was pretty interesting. So to plot it differently, so that's exactly the same results, but after 0 hours, so the first measurement, and after 29 days, so you can see a bit better. And you can see on the bare silicon, you have this peak appearing. And here we plotted the actual area of below these curves. And you can see that only for porous silicon, bare porous silicon, you see an evolution of this area. So this work was performed by Irene Carrasco, who works at the ISMAN laboratory. With us and with this ISMAN engineering school in Le Mans. So basically, we validated that titanium dioxide is protecting, which is good. And it's good also because it's an earth-abundant material and it's not toxic. So this is something currently in debate in the scientific society. But so I'm not specialist, but it's known to be not toxic. It's used in for implants, for instance. So I think it's fine, but maybe something is to be verified here. So ALD layer, even the thinnest ones, can prevent oxidation. When you do only one cycle, the risk is to not have an homogeneous layer, or to leave holes in the layer. So we were using only 5 cycles. Maybe it's possible to go below, but it's not so easy. And thermal ALD, which is the normal without plasma, can coat these pores, even 30 micron thick layers. Probably it can coat thicker ones, but we didn't go further. What about the catalytic performances and the plasma capabilities? That's something we will discuss after. So the first thing is indeed, what about the catalytic activity? So we are not a lab specialist in photocatalysis. That's why we're working now with the people in Catania. But anyway, there is a quick test to perform that, is to use methylene blue degradation. So basically, you expose your sample, or you put your sample within methylene blue solution, and with catalysis, with catalyst, you can degrade methylene blue faster if the catalysis is efficient. And then you can only, by measuring the absorbance spectra, you can see if, or you can calculate the concentration of methylene blue and know the degradation rate. So that's what we've done. So with this parameter, so we exposed our sample to UV visible lamp, and we've performed every 10 minutes the measurement. So you can see here it's a bit more visible here. So at the beginning you have this methylene blue. You can see the porous silicon sample there, and after some point, like 2 hours, you already have more than 80% of degradation of methylene blue when you have the thicker layer of titanium dioxide. And when you have the thinnest layers, you can have also degradation compared to the control solution, which is when you just use methylene blue without any catalyst, right? It naturally degrades, but of course, thanks to titanium dioxide and porous silicon, we were able to show that it degrades faster with that. So this is the details on how to calculate the degradation as a function of the concentration of the solution, right? So we can discuss the details if needed, but it's very common in the field. So basically, we can see that for the 1 nanometers or less layers, we have similar degradation kinetics, which is interesting. But of course, after some time, the control solution reaches the same degradation point. This means that after some time, for the thinnest layer, you have saturated all the photocatalytic sites, so you don't really do anything anymore. While for the 10 nanometers, very efficient and much faster. Okay, I mean, I wouldn't say very efficient because, of course, compared to proper catalysts, it's not great, but still, it's interesting to see that thanks to the porosity and the titanium dioxide, it worked. So yeah, that's basically it. So it's possible to, thanks to ultra thin coatings, so limiting the number of material you use and so on, you can have efficient degradation. And of course, well, thicker layers are more efficient because they have better crystallinity. So we need to check what's happening on the porous layers. So that's a collaboration we have with Tyndall Institute in Ireland. And so the rest of the study will hopefully be published soon. So keep reading the literature. So now I'm doing this last part regarding the optical characteristic. Can we really tune the band gap? And of course, I noted the catalytic activity is actually not high, of course, but it's good. So to check if we were able to change the band gap to adjust to the good reaction we want, we've done UV-Vis measurement. So this is 10 nanometer titanium dioxide deposited on silicon. You can measure the reflectance, and thanks to kind of calculation, you can extract the band gap. So for 10 nanometers, we had almost 3.2 EV, which is in agreement with the literature for the anatase phase of the titanium dioxide. And now to check in the pores, we need to perform advanced XRD. It's something we are currently doing with Fabio Piccinelli at the University of Verona, but it's something quite tricky to do. So, and again, if you yourself you know how to do it, we are happy to talk. So okay, we are happy we were able to have a good catalyst. But can we tune this? And especially we would like to reduce a little bit the band gap. because it's a wide bandgap semiconductor, and it means it's efficient only in the UV. Okay, so if we're able to lower it a bit, it would be great. So what we've done is we've performed rapid thermal annealing. So after the deposition, so at 600 degrees under nitrogen, oxygen, and a mixture of nitrogen and oxygen, to see if we were able to kind of dope the layer with this nitrogen oxide and see what was happening. And what happened is we managed to actually increase the band gap slightly. Okay, so the post treatment doesn't help to reduce the band gap, but still it means if your application is to increase the band gap for whatever reason, it's possible. So post annealing doesn't reduce the band gap. So now I'm moving to the perspectives, especially because I'm also running out of time. But it's almost done. So how to properly adjust the band gap? That's now our question and the things we're working on. So there are basically two possibilities. Either you do multi-layering, so you could add a layer with a band gap in between the silicon and the titanium dioxide, so it helps to the electrons to flow, and it's much better. But of course, when you check this kind of materials, they are not always earth abundant, or they can be toxic, or okay. I had the discussion with some people before. They would say that cadmium based materials are not toxic because they are encapsulated and so on. Fair enough, but still I think if we can avoid this, it's better. So you need to find a good balance, and but it's a possibility, definitely, and you can find other ways to tune it and so on. But the method we are working on now, since we are working on ultra thin layer, is to try to do a plasma doping, so to directly in situ dope our ALD layer thanks to a plasma. So you can do nitrogen plasma, for instance, and you dope it. The literature showed that with nitrogen doping, you can reduce the titanium dioxide band gap. But many people say, okay, plasma ALD is not as conformal as thermal ALD, which is true, but no one really is interested in forming plasma within pores. I mean, it's not true because you see in the literature we have a couple of examples, but doing a plasma within porous silicon, you have maybe more experience than me in PSST conferences, but I don't think it's so common. So I think now it's a nice field of investigation. How does the plasma form within the pores? So that would be our next questions. And of course, so we need to develop. There is a lot of space for development. Okay. So here I have I have this question. What about fuel production? Do we manage to produce fuels? Well, actually, yes. It's not very convincing, this video, but we can see here a few bubbles. Okay. So we managed to, thanks to porous silicon coated with titanium oxide and a solution containing diluted CO2, we managed to produce gas, but it was such a small amount that we don't know what it is exactly. Did we manage to tune the band gap as needed? Well, to be honest, I don't think so. But still, you see that it's possible to have first results. Okay, let's move to the conclusion. So ultra-thin coatings allow both passivation and photocatalysis when deposited into porous silicon, which is, I think, a good point. So, of course, it's not the first example of that in the literature, but having such thin films, I think it is, to be honest. And but you see that there is still a lot of space and for investigation to try many applications for the porous silicon or silicon carbide community. You can do modeling, experimental, and fundamental science. So if you're working on porous materials, you can investigate many fields, and some application can be motivating for the for outstanding findings. So the one that motivates me is the electrode development for CO2 valorization. But of course, you can have hundreds of application in the medical and so on uh, where ultra thin coatings can be good. So you see, many I've showed you before, many things ongoing, and to develop all these things for using green fuels or fabricating green fuels, well, help is welcome. So thank you everyone, especially to these people. So Gael, Thomas, Irene, Bashar, Lisa, Matteo, Vanessa, Jan, and Kaushik. And thank you, of course, to the Netpore network for inviting me. And I think the next one will be Anne Chantal. You met her probably at PSST. She won a nice prize, so she will be the next one to present. So thank you, and of course I'm open for questions.
Thank you very much, Brice, for your very, very interesting presentation and this great overview of the field also. And yes, and thanks for mentioning Mrs. Happy from last PSST as
Yeah.
Chantal Gouget. This is great. We have time for questions. Any question? Yes, you can either start talking or raise your hand. I don't see any. Do you have? So, Bruce, I may have a, a question. I don't know, maybe you mentioned it, but I'm not totally sure. I was wondering the influence of the pore diameter in the wall system and its
Yeah.
performance.
Yeah, that's a good question. So initially, we were very cautious on that. That's why we started developing the deposition in macro pores. So that's the main picture you've seen a couple of times in the presentation.
Yeah,
So with these balls, so that were micropores.
yeah,
I can't
I know
find it, but
yeah, you do that, but at the end with the plasma doping, and I was just curious if.
yeah, yeah.
So,
So then we work mainly on mesoporous, so much thinner pores, and it coats perfectly as well. So the coating is fine. And for the etching or I mean the exposure to the water, it works also because it's possible to remove, for instance, silicon dioxide. So we know also the water enters the pores. So either for coating or for catalysis, we know it's possible with thin films.
yeah, that's very interesting.
Yeah,
And another question I'm thinking of, doing a surface chem uh, for our application. The CO2 that you detect in the very last part on the video,
yeah,
but you detect the fuel, but the CO2 you try to
yeah.
recycle. Uh, are you sure it's just you mentioned that it goes well into the pores? Because
Yeah, here is the CO2 touching the pores? That's what you mean?
yeah,
Yeah.
what I'm thinking is CO2 is diluted in water
Yes.
in
I
this
mean,
way.
actually, it's a solution of KCO3.
Okay, because
Yeah.
I was wondering if you infiltrate the pores well
Yeah.
enough because you have this nice coating with TiO2 and things inside. But the same story than when you etch mesopores with HF, you need
Yeah.
ethanol just to infiltrate the pores. And I was wondering if you don't need any surfactant
Surfactant.
like.
I
Uh,
don't know. Actually, it's true. It's a good question. I think it's the pores are still wide enough, but I have no proof. I also know that titanium oxide doesn't really affect the wettability. Okay, so if it would have been hydrophobic, for instance, maybe. But yeah, so far I can't really prove it. So maybe it's a surface reaction, and
Because
yeah,
yeah, that could. because even if you have quite large pores,
Mm.
if it doesn't wet enough, just if it doesn't
Yes,
infiltrate, we observe that it's a different system, but with bio, whatever you have for
yeah,
biosensors, when it's very diluted, because
yes,
you don't, I don't know which concentration of CO2 you have, but it also depends on the concentration you have. It's
yes,
like a sensor. If you want to sense a very small amount of analyte
yes.
with a high surface, that's great. But if the high surface is not in contact well
Yeah,
with,
yeah, definitely.
you
Yeah.
have to amplify it
Yeah,
somehow.
I
Yeah.
don't know. So, of course, for this experiment, we were using very, very concentrated CO2, or
Yeah.
but of course, I don't even know how to probe this. So maybe you have ideas how to know if it's really in contact with the catalytic site.
How
I
to
don't.
optimize the interface
Yeah.
because your system.
What we know is, for instance, with methylene blue, it
Yes.
worked because we can see that when you use the coated silicon, porous silicon, it increases. But for CO2, I don't know if there is a difference.
Yeah.
Hmm.
It's very interesting. It's
Yeah.
a great.
Sorry, there are three questions on the chat.
Yeah. Okay.
Can you read it?
Yes, probably. No, I don't know where to find them, but
Uh,
yeah, yeah. I think
I can, I
okay.
can.
Is the technique
Okay.
limited to by gas? Okay. So gas phase is of course interesting because you directly convert the CO2, uh, but you need to bring more energy. It's already difficult to perform the CO2 reduction, but if you are in gas phase, you would need to heat and to increase the pressure. There are already existing systems, and so that can be a problem. So it's possible. It was actually my first idea, but then I thought it can be safer and easier to make it like this. But it's possible, and with porous silicon carbide, since it's used in catalytic exhaust, for instance, in the cars, it's definitely possible in harsh environment. But for porous silicon, I'm not so sure. Can the deposition on organic can we do organic? So I'm not sure about the question. Is it depositing organic material, or is it depositing on organic materials? So if the question is on organic materials, yes, it's possible. So ALD is actually a chemical process. So it's you need to absorb the molecules on top. So there are many examples of ALD coatings on any 3D surfaces. So even if it's rough, it works. So it's possible. If it's depositing organic materials, it's possible. It's called MLD, molecular layer deposition. So it's slightly different. It's a great. It's a field I would like to try also. So yeah, it's very nice. You can use organic precursors, and it works. So and the big trend now, there is a very famous researcher um, called Marita Karpinen, I think, in Finland. She had like two ERC grants, I think, to develop hybrid structures. So organic inorganic by MLD. So it's great. So yeah, you can prepare core shell particles with ALD for sure. Can the technique be used to control the layer morphology? Uh, so I'm not sure what you mean. Maybe it's well, you can probably it's a coating, right? So ALD is really meant to be conformal. So the idea is not to change to make the layer smoother. Actually, that's not my aim. For this, I would recommend another deposition like CVD. It could work, but of course, it changes the morphology. So if you see the balls I've shown, they are very different from the pore. So it changes. But can you control it? Not so sure at this scale. So yeah, the question was actually depositing titanium oxide on organic materials. Yes, it's possible.
Any other question? Okay. So if we have no more question, then I suggest to thanks our speaker again. Thank you
Thank
very
you.
much, Brice, for your nice presentation. And we meet again in not in a month from now, because it will be summer break for most of the people, but in September we come back for the new session of webinars, Netpore webinars. And I wish you all a very good day.
Yeah, and don't hesitate to contact me if you have ideas on all the questions I've asked. So it would
Thank
be
you very
helpful.
much, Brice. Thanks a lot.
Thank you.
Have a good
Thank
day.
you. Have a nice
Bye-bye.
day. Bye.